logical connectors can be represented visually. The complement of an event is the collection of outcomes that are not the event. Going back to our spinner example, if we spin the spinner and land on blue, the complementary event is landing on anything other than blue. Another way of thinking about it is everything that's not blue, or everything that is not the event A. When you add the probability of an event A to the probability of the complement of the event A, the result will always be 1. It's sometimes easier to determine the probability of A using this method. So here you see the probability of A plus the probability of not A is equal to 1. These two graphs are Venn diagrams that represent the two situations of A and not A. We'll look at those in a little more detail now. If we were to represent A in this diagram, it's everything that is within this circle space identified as A. The complement of A is everything that is not A. So in that case, it's everything that's outside as well as everything that's in B, because if it's just because it's in B, it's not part of A. However, we don't go anywhere into the A space, so everything that is not A. Now this is A intersection B. So it's, remember that's A intersection B is the same as A and B. So we're looking for things that are in both A and in B. And in the case of our diagram, that's the place where the two circles overlap. A union B, otherwise referred to as A or B, is everything that's in A or it's in B. So it's everything that's in A and everything that's also in B. So it can be any part of that space. The complement of A, or not A, is everything that is outside of A. A intersection with the complement of B. Let's think about this a little bit. So we start off with, we want the spots that are part of A and part of everything that is not B. So everything that's not B is everything that's outside of the B area. But we're looking for just the intersection of where that defined area, so all of that space outside of B, is also intersecting with A. So it has to be outside of B, but it has to be inside of A. So with that you get the moon shape within A. The complement of A intersection with B. Similarly, everything that is not A, we start off with whatever is outside of A. All of that area outside A, but we want wherever it intersects with B. So we can simplify it a little bit to say it's the area outside A, but it also has to be inside of B. So again, we get the other half moon. A union complement of B. So this is A or everything that is not B. So everything that's not B is all of this, everything that's outside of B, and it can also be within A. A union with the complement of B. So we can look at, because it's an OR situation, right? We've got the union, which means OR. So it can be in A, so everything that's in A, or in everything that's not B, so everything that's outside of B. And once we've defined that, now we can go and identify that's all of the space. Complement A union with B. So that's everything that is not A, or it can be in B. So that then allows us to bring in part of A since it can be in B. And everything that's outside. The complement of A in union with the complement of B can also be written as take the intersection of A and B, so that's the intersection instead of union. take the intersection of A and B, but do the complement of that. So sort of like take the intersection and then take everything that's not the intersection. Let's see how that works out. So the complement of A is everything that's outside of A. Then the complement of B is everything that's outside of B. So the only places that is excluded is that white space in the middle. Finally, the complement of A intersecting with the complement of B. So that's everything that's outside of A, but is also outside of B. You can also do Venn diagrams with more than two events. In this case, we've got three. If you've got something like A intersection C, that's everything that's in A and in C. If you've got the complement of C, that's everything that is outside of C. B union C, so that's everything that's in B or in C. So it's everything that's in B, or it can also be everything that's in C. Finally, A intersection with the complement of C, so that's everything that's in A and not in C. So it's got to be in A, but not in C. So this is in A, but we stay out of C. Now let's look at another example. You roll two dice that are six-sided. What's the probability that the number that lands face up is different on the two dice? So we let A be the set where we're landing on two different numbers, and the complement of A is landing on the same number. So I'm going to start off by filling in the list of numbers that fall into the complement set. So that's when I've got 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Now in the A set, so I've got a 1 and a 2, a 1 and a 3, 1 and a 4, 1 and a 5, 1 and a 6, then a 2 and a 3, 2 and a 4, 2 and a 5, 2 and a 6, then a 3 and a 4, a 3 and a 5, 3 and a 6, then a 4 and a 5, 4 and a 6, then a 5 and a 6. So that's assuming that dice 1 started off with a 1 and the dice 2 had a 2. And now we flip them around as if they went the other way. 2 and a 1, 3 and a 1, 4 and a 1, a 5 and a 1, 6 and a 1, a 3 and a 2, 4 and a 2, 5 and a 2, 6 and a 2, 4 and a 3, 5 and a 3, 6 and a 3, 5 and a 4, 6 and a 4, and 6 and a 5. So A has a set of 30 and complement of A has a set of 6, which makes sense because there are 36 possible combinations. Each dice has 6 faces, and you have 2 dice, so 6 times 6 gives you 36 possible outcomes. So the solution set of the complement of A is equal to the set of 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. There are 6 events in the sample space of complement A. We figured out that there are 36 possible solutions in total in the sample set. Therefore, we can conclude that the sample space of A will have 30 events in it, which we identified when we did the Venn diagram. Using our understanding that the probability of A plus the probability of its complement is equal to 1, we know that we've got 6 out of 36 is the complement, so the probability of A plus the probability of the complement, which we said is 6 out of 36, is equal to 1. Probability of A plus 1 out of 6 is equal to 1. Therefore, the probability of A is equal to 1 minus 1/6, which is equal to 5/6. Therefore, the probability of landing on two different numbers is 5 over 6. Events are called mutually exclusive if they can't happen at the same time. As an example, if we're spinning a spinner one time and event A is spinning blue and event B is spinning red, those events are mutually exclusive because they can't land on blue and red at the same time. In a Venn diagram, two mutually exclusive events do not overlap, or if the circles are drawn as overlapping, there's nothing in that overlapping section. Add this to your memory aid. Try the practice questions in the workbook and check your answers against the answer key.